Okay, so yesterday we talked about torque. I think, double check, but I think we got the formula for torque. T equals F D sine of the angle. There won't always be an angle, but if there is, then you know what to do with it. And did I have you guys put it on your card? Okay, all right, so we're good. So we are ready to talk about the sine of torque. First of all, we should know that torque is a vector quantity. And I'm going to ask you the same question for the millionth time. What does it mean to be a vector quantity? What two things do I have to have? Celia? Direction. What else? What's the other word? Cadence? Magnitude. So most of the time, we're concerned with the magnitude. We want to know how big, how much torque. But we have to take the direction into consideration. And with these problems, lots of times it doesn't say clockwise or counterclockwise. You have to look at a picture to figure it out. So when we're looking at the rotation, of an object with torque, we follow the same rules that we did with a rotational object, with any rotational object. So if I'm going counterclockwise, see if you can remember. Was counterclockwise the positive or the negative direction for a rotational object? Okay, so if I'm going counterclockwise, then I treat it positive. And if I'm going clockwise, then my direction is negative. And you just have to assign those. It's not going to say that in the problem. And usually you'll have to look at a picture and they'll be like up arrows or down arrows. You just have to pay attention to that. And we're going to look at one here in just a minute. So if you have a diagram, and most of these are diagrams or pictures, you have to look for the force. Sometimes you have to pay attention to gravity. And you have to look for the direction. Now, if you get a really nice problem, all those things will be labeled for you. But sometimes you'll just get some words that ask you a question and then a picture. And you have to figure the whole thing out. If you have a diagram, I'm just going to use the word diagram, with multiple forces causing the rotation. So listen to what I just said. If you have a diagram or a situation where you see multiple forces causing the torque, what do you think you're going to have to do with those multiple forces? If ultimately they're what's making it move, what do you think, Cadence? What? Find equilibrium, is that what you said? Equilibrium or equilibrant? Okay, so how would I do that? Anybody know? What did we do before when we had multiple forces? What did we call it? We had a formula. We called it F what? What makes the motion happen? The total force or the net force? Net. So we're going to do the same thing with this. So if I have that, I have to find the net force. Because remember, my formula is FD sine theta. So I have to figure out what the net force is. And to do that, I have to treat each force separately. So if I do that, then I'm going to end up with several different formulas where I have like T1 equals F1 D1 sine theta. And it actually has to be labeled like that. Or T2 equals F2 D2 sine theta. And technically this would be angle 1 and this would be angle 2. So there will be multiple angles that you have to work with. Some of them will go, I mean, we can go as 5, I don't think you guys will have any more than like 5 forces on an object at once. But in that case, I would have to work with all of them. And I would really have to pay attention to that direction and whether it's positive or negative. So, when I talk about, okay, let's talk about Thanksgiving. How many of you, like my grandma was always big on this, cook the turkey and you dig that wishbone out, or the turkey breast, there's a wishbone in the front of it, you know what I'm talking about? Oh my gosh, you gotta do this, people. And then you find someone and basically you two have, it's almost like a thumb war, you put your thumb on the wishbone and you pull. And whoever gets the side that has that top part of the bone gets to make a wish. Woo, that was really exciting when you're a child. Okay, so what happens when we're pulling on that wishbone? One person is pulling this way, right? And the other person is applying a force in this direction. So one force is counterclockwise, yeah? What's the other force? Yes, so what happens? The person with the most force snaps the wishbone, but the net force is what makes the wishbone snap. Does that make sense? The forces are in opposite directions. The one that is larger is going to cause the wishbone to crack. So I have to pay attention to my positive force versus my negative force to get my net force on a rotating object. Because truly, when you're applying that force to the wishbone, that's a torque. How many of you have ever changed, like, used a wrench to change, or even a socket, to change something on your automobile, or I'm trying to think in your house what you would use that for? A pipe, a fitting on a pipe. Anybody ever done anything like that? Yeah, that's torque, people. People use it all the time. So it's something you should be able to relate to. So basically what I have to say when I look at this is that, we're going to write it like this. T net for net torque is equal to, what does that mean? That sigma? Yeah, the sum of the torques. So I write it as, just like what I did, T1 plus T2 plus T3, on and on and on and on. What does this really become? How do I find torque? What is a torque? Three things I have to multiply. Jaden? What? Oh shoot, no, not mass. Okay, can somebody help him? What am I applying? A force over a distance. Good. There are cases where this force, gravity acting on a mass, That's a force. What is that also? Gravity acting on a mass. A weight. So sometimes this will be W, or really mg1 times d1 times sine of theta 1. Plus, and I'm just going to write f2 d2 sine 2 plus f3 d3 sine theta 3. And it could go on and on and on. You have to pay attention to the movement, because technically this guy could be positive, negative, positive. You have to pay attention to how the torque is moving. If you properly assign the convention, which means if you make it properly positive or negative, your answer will have the right direction. You won't have to do anything to it. It'll work out as either a positive torque or a negative torque, which tells us the net movement is either going to be clockwise or counterclockwise. Make sense? All right, I think, yeah. I didn't grab one. Let me grab one of these papers. Okay, let's look at this. This is going to be a little small up here, but you should have that paper. So I want you to pay attention. I want you to look at this. And I don't want you to talk to me about it. That seems a little fuzzy. Oh, it doesn't like that. Okay, so what I want you to look at first, and I want everybody to do this, I want you to look at this arrow. That's my force arrow. And this is my second force arrow. So I already have, within this system, and these are oftentimes going to have pictures. Within this system, I already have an F1 and an F2, right? Now I want you to think about this. If I apply those forces, what way are they going to make that object move? And I want you to tell me, or I want you to write it down. Let's make F1 and F2. And I want you to look at those, and I want you to give me the force with a positive or a negative based upon the way you think that wheel is going to turn, clockwise or counterclockwise. So when I look at that first force, it's the 15 Newton force. It's an upward force. Is it going to make it turn clockwise or counterclockwise? Callie, what do you think about force 1? Clockwise or counterclockwise? Clockwise. Do you agree with her? I do too. So I'm going to write down 15 newtons. Would that be a positive or a negative if it's going clockwise? Good. Now look at your second force and ask yourself, clockwise, counterclockwise? This is a nice one because I don't have any angles I have to worry about. What do you think, Jaden Waddy? Clockwise, counterclockwise?
Clockwise.
Clockwise. So I'm going to make it negative 11 newtons. So now I want you to find your D1 and your D2. Noah, what's my D1?
Oh, is it the 0.14?
Yep, 0.14, I would put my 0 in there, 0.14 meters. And then, Marissa, what's my D2? 0.07 meters. Okay, so now, what I'm really being asked for is my net torque, right? So I have to take my sum of my torques, and I have to set them equal to F1 D1 plus F2 D2. So the sum of my forces are equal to negative 15 times 0.14, oh, I should put my newtons in there, times 0.14 meters, plus negative 11 times, oh my gosh, negative 11 newtons times 0.07 meters. And that's the sum of my torques. So now I got to punch that into a calculator if I can find one. Put it in, see what you get. We'll see if we all agree. Oh, I know what I need to tell you on this because it will become important. Everybody stop right now and get your calculator back to degrees. Because when we start using angles, you're going to have to be in degrees again. And I think there might be one of those on your home or on your problem solving stuff. Kara, what'd you get for an answer? Negative 2.8? 87. So we need 2 sig figs. So negative 2.9 newtons times meters. Now, see if you have questions about that. Jaden Hatcher.
I was close, I got like 2.7.
Okay, I didn't actually multiply. Let me do it. Negative 15 times. I got 2.87. So check how you put it in your calculator, which I think is exactly what Kara said.
So there's no combined units for it?
It's just Newton times meters. It's called a Newton meter. Okay.
I got it.
Okay, good. So now, if you look at your handout, I want to look at this really quick. I think 1, 2, and 3 are pretty straightforward and easy. Let's look at number 3 together. If I go down to number 3 and I read number 3, it's asking me to calculate a torque, but I'm given an angle. So you might, like next to this one, remember you're going to have to use FD sine of theta because you're given an angle. All of these forces that we're working with right now are going to be in the y, or the vertical direction, so we're always going to be using sine. A little later on, we'll see if we get to a point where we're going to add in that horizontal component of torque. But we need to get through this first. If I flip it over, I have a picture. And I want you, let me see if I can find that. There it is. Well, let's at least label this starting point, where that 30 newtons is. And because that is starting point, that force is being applied at 0 degrees because it's starting. So we treat that as 0. There's no, it's not moving yet, so we don't have to worry about that. Yeah, this one, this force right here, that's where we're starting. But it's not moving yet. So then I actually have a force up here, and I actually have a force here. Yeah.
So then what does the 45 degrees go for?
The 45 degrees is going to show, and I'm going to talk about that in a minute. So let's make this stop. Let's make this arrow my stopping point. So then we have to analyze the motion of what's going on. this line right here is a hash line, is telling you, do you see that O? That's telling you that this lever was pushed to here before anything was really taken into consideration. So what we want, that's what the O tells you, and that's what this angle here tells you. The machine started and it moved to the dotted line. Once it's at the dotted line, it continues to move, and it's moved 2 meters. So there's my 2 meter mark. Do you see how it's divided up into 2 meters down below? So that's telling me that this, I'm trying to read it, 31 degrees, 25 newtons happened over 2 meters. These diagrams are a little tricky to read, so be sure you're paying attention. So that's what that's telling me. Then as I move down, do you see the other hash line? That's telling me, if I look at from where it started all the way over to that hash line, it's moved how many meters? From where it started, yeah, 4. So here that's telling me my distance is 4 meters. My force was what? 10 newtons. And it happened, or when I want to know about this, was at 23 degrees. So then that gives me my angle. I only gave you one of those today. Tomorrow I'm going to give you some bigger pictures where you can see things a little better. I wanted to walk you through one today. They're not all set up as, I don't like how this particular diagram is set up all that well, but it gives you all the information you need to start a problem. Jaden?
I guess this is just this picture is kind of confusing. How is, so where you said, when we were at 31 degrees 25 newtons, right, and 2 meters, are we starting at from where you do that little...
Yeah, the hash line tells you, basically, this is what the hash line tells you. We're really measuring, this is also 31 degrees, and when we measure from that 31 degrees to this 31 degrees, now it doesn't look like it when I draw it because I didn't draw a true angle, we've covered 2 meters.
It just looks like it's more than 2 meters. Like just...
If I go straight up and follow it down, it's 2 meters. This is saying that this force right here was applied over here to make it move through that 2 meters. So the force that made it move that 2 meters was applied from the starting point at an angle of, I've marked over it so much, 31 degrees. Yes.
Wait, so then the hash mark is technically our starting mark?
The hash mark is what?
Technically
Yes, yes, in this particular diagram. Tomorrow, what we're going to do, I'm going to have a bunch of pictures. Most of them are more clear with this than this one. And we're just going to practice picking out our forces, our angles, and our distances for a little bit. But I wanted to work you through that one so you could sort of see how you pick them out. You won't have a whole lot like this. I personally think, or like, even if this force was applied at an angle, I think those types of diagrams are easier to read. But I'll give you several tomorrow. So basically, all I want you to do today is try to get 1 through 5 finished. Let me check your answers and let me help you if you need help. You can do it in problem-solving groups if you would like. And then I'll collect this one tomorrow for a grade, but it won't go until next quarter. The other stuff.